This content was taken from our groundbreaking heat pump and system design training. Engineers that take this course and pass our rigorous verification process are arguably the best engineers in the country and capable of designing and installing the most efficient heat pump systems possible. And they can be found at heatgeek.com. Heat pumps simply move heat from A to B. If you're cooling the property, you're obviously moving heat from the inside of the property to the outside. When moving heat into the building, however, the actual heat source can vary. For example, you could source heat from the ground, air, water, or in the case of commercial properties, anything else that's being cooled, such as a server room or commercial fridge. By far the most common source of heat energy, or sink if cooling, is air. To extract heat from the air, we essentially use a radiator, like a combustion car engine, with a fan blowing over it. These come as monoblock or split units. Split units were historically the most common. As the name suggests, these units are split into two. They have one outside with a condenser or evaporator, aka a fan coil, and another unit on the inside with a condenser/evaporator, fan coil, or a plate heat exchanger if they're going to power a water-based system like radiators or underfloor heating. The compressor and expansion valves are located on the outside units for noise and space. A refrigerant gas is what carries the heat between the two units and needs to be carefully injected into the system by a fridge gas engineer. Again, the indoor units can either have fan coil units, like the unit outside. These are known as air-to-air heat pumps, or they can be connected to water to run around radiators for air-to-water heat pumps. The main advantage of these split units is that you can site the indoor unit quite far away from the heat source, and so they're very helpful for commercial buildings. A monoblock system is becoming the unit of choice for air source heat pumps connected to radiators and underfloor heating. These have both condenser and evaporator elements outside and sometimes incorporate a system pump as well. Because these don't have custom-built fridge lines going into the house, they don't need to be filled by a fridge technician, and so save time, cost, and risk. The benefits of delivering the heat to the property via air are that the building is heated up faster and there's some air filtration and air conditioning. However, they are generally less comfortable for living spaces. If we're delivering this heat via radiators or underfloor heating, low temperature radiant heat delivery is slower to heat up, but suits a more stable environment and is more comfortable for stationary occupants. If siting the outdoor unit is difficult though, you can use the ground as your heat source. Ground source heat pumps were historically more efficient than air source, as the ground temperature is a lot more stable than the air. And as most of the heat is generated in winter, having a ground of around 12 degrees Celsius increases efficiency. However, recent improvements in heat pumps have recently really narrowed the gap and put air and ground on a much more level playing field, particularly with lower flow temperature systems. The heat source temperature is much less important than what it used to be, with a higher importance placed on the flow temperature required for the radiators. In other words, hydronic design, such as what's taught in the Awakening and Mastery courses from HeatGeek. Collectors are pipework that ground source heat pumps use to collect or deposit heat into the ground with a heat transfer fluid. Historically, this was made up of a mixture of water and salt called brine. The addition of salt lowers the freezing point to around -20 degrees C to enable the ground loop to run around 0 degrees without any risk of freezing and damaging the equipment. This is the reason a ground source heat pump collector is still called a brine loop and the circulating pump called the brine pump. These days we use a mixture of water and glycol mixed to a freezing point of approximately -15 degrees Celsius. There are two main different types of collector: vertical arrays and horizontal arrays. Horizontal arrays need space. Horizontal arrays are where trenches are dug up around a field and pipework is laid in, which will extract about 10 to 18 watts per metre of pipe, however, needs to be calculated. They can be laid in a single pipe configuration, a double pipe configuration, vertical or horizontal slinky, or a compact collector. Trenches can be dug up in different patterns, but importantly, the more concentrated they are, the lower the efficiency and the more risk there is of freezing the ground, which is literally disastrous. The best and most efficient formation is the largest single loop pipe possible, covering as much ground as possible. The least is a compact collector. The greater the surface area used, the less issues and the highest efficiency. And as such, slinkies and compact collectors are rarely fitted, if ever installed at all now. A full ground survey should be complete to check the ground is suitable before the works are done. The ground should be conductive, which requires moisture. Dry ground will conduct less heat. Holding water is not enough though. The water must move and replenish. As such, both the porosity and the permeability will need to be approximately understood. Vertical arrays or borehole loops are again split up into two types of collectors, open loop or closed loop. Closed loop is where a borehole is drilled down circa 80 to 120 meters into the earth and a casing pushed down to stop the collapse of the borehole. A collector pipe with a 180-degree bend in the end is then dropped down with a weight. A grout is then backfilled using a tremie pipe to ensure there is no collapse and to ensure the best contact for the thermal transfer with the ground. The installation will need approximately 40 to 60 meters of pipe per kilowatt load required, but needs a full calculation. Several boreholes will be needed for a typical house, the number of which really though depends on how deep they are, and a full geological ground survey again is essential. Open loop vertical arrays make use of aquifers instead of using a brine mix. Imagine aquifers as underground lakes where water slowly moves from one end to the other. One pipe goes upstream collecting water and pumping it to the heat pump, and it's then returned further back downstream. The advantage of open loop is that there is slightly better heat transfer into the heat pump system. However, the pump needs more power to draw the water up, and it can be difficult to get right, so needs experience and a specialist, and does need more maintenance, as there's a filter to clean on a regular basis. Open loop and closed loop are also used for water source. Water source extracts heat energy from any river or lake. The rate at which the water replenishes in relation to the load it's trying to apply is very important. For example, a large lake for a relatively small load, say 5 kilowatts, shouldn't need much if any replenishment. A much larger load and smaller lake will need a constant supply of fresh, more heat energy dense water to stop the lake freezing up and the heat pump grinding to a halt. Like ground source, this can be open or closed loop with the same pros and cons of the filter cleaning and improved heat exchange between the two options. Pump power consumption isn't as extreme though, as it doesn't have to fight gravity. Also, similarly, a consideration should be given as to where the water is taken from and returned to avoid recirculation. In the case of a lake, take from the top and deliver the colder water to the lower levels, with rivers again taking from upstream and deliver the expended water downstream. The last variant of heat pump to be aware of is high temperature heat pumps. As the name suggests, high temperature heat pumps produce higher flow temperatures, which can be helpful when heating more difficult properties that may have limited space for emitters or restricted insulation. High temperature heat pumps achieve this with two compression stages. The second additional stage taking a separate refrigerant to a higher temperature. These are less efficient, however. The higher the flow temperature required, the lower the efficiency. Always. Thankfully, recent improvements in refrigerants such as R32 and R290 have meant higher flow temperatures of 70 degrees C can be achieved with one single stage compression and also with improved higher efficiency at higher temperatures. This full course can be found at courses.heatgeek.com, and don't forget to comment with any questions you might have, as well of course please subscribe to the channel. We'll see you on the next one.